Hey, this is Angela Galloway, and I am going to work with you today on Chapter 3 from STA220. Chapter 3 is where we actually start summarizing our data, and so it's called numerically summarizing data. So we're going to look at creating our parameters or our statistics. So I'm just kind of going to go over some of the highlights from this chapter. Of course, if you have any questions, you can always email me at angela.galloway@kctcs.edu, or if as you are working on a problem in the My Stat Lab, you're having any problems with how to solve the actual problem you're working on, you can always click the Ask My Instructor, send me an email, and that will send me the problem you're working on as well as anything you want to type in to tell me what you're having issues with, and I can get back to you on that. So looking at this in chapter 3, at the beginning, we're looking at measures of central tendency. So what we're trying to do is when we're describing a distribution, some of the main things we want to know about is first, which we talked about in chapter 1 and 2, looking at what is the shape of the distribution. So is it symmetric? Is it skewed? That kind of information. Is it unimodal? Is it multimodal? So all that information is going to give us something about the shape. But when we get into measures of central tendency, we're looking at where is the center of the distribution. So, okay, I know it's a symmetric distribution, but is it centered at 5 or 500? You know, where is the center of this distribution? So where is most of the data centered around? So the most common measure of central tendency is going to be the mean. So we pretty much all know what the mean is, right? That's the average of a group of numbers. So with the mean, with the population mean is called mu, so it's a Greek letter. We generally have that whenever we are working with population parameters, we're going to have that Greek letter usually used. So we've got the mu there, and that's the Greek letter M. And so we see that this is going to be the formula for that. You just add up all the numbers, divide by the total size, sample size or population size that you have there. For the sample mean, we call that X bar. So that's X with the line over it. That's going to be a statistic. This is going to be a parameter, right? So statistics come from samples. Parameters come from population. So our mu is a parameter, X bar is a statistic. The median is something we're going to use, we'll talk about in the next few slides. We might use the median to describe the center of the distribution. The median actually shows us the middle. It is denoted by M. To find the middle, you know, sometimes you can just write out the numbers like I'm showing here. If our data set was just 1, 2, 3, the middle number would be 2, right? That's what falls in the middle. If our data set's 1, 3, 5, and 7, the middle is somewhere in between 3 and 5, right? There's not an actual observation that's in the middle. The median is just going to be in the middle, in between those two numbers. So what we do in that case is we take 3 plus 5, divide by 2, and that gives us 4. So the median in that case would be 4. Now we do have a little formula that we can use to find the median, and that is n plus 1 divided by 2. Now what's important to note is this does not actually give us what the median is. It tells us which observation is the median. Okay, so when you use this formula, it's just to tell you which observation is the median. Once you find that, then you would go back to your data and count and see which one. Like this one is in the second place, so we'd go to 1, 2, and then 2 is our median. So this is going to tell you which observation is the median. Now, I don't think you're going to do a lot of these by hand, doing the average or the median. What you're probably going to be using is your one variable stats in your calculator, or using the StatCrunch where you can use those descriptive statistics and get the data from there to find your statistics or your parameters that you need. And we'll go into that in a minute. The last thing that we talk about with central tendency is the mode. We talked a little bit about the mode back in chapter 1 when we talked about modality. So something being unimodal meant that it had one mode. Something that's unimodal, you know, look like this, where it had one highest bar there. And so this would be a unimodal distribution where there was one number that was occurring more than any other. Something like this see, like that would be multimodal. We see the two peaks there that seem to be occurring as often as each other. So those would both be modes. So now we're talking about actually what the mode is. The mode is the value that occurs with the greatest frequency in the data set. So that's where those terms modality, unimodal, multimodal all come from. It's possible that you won't have a mode. You can have a data set that doesn't have a mode, like there's just not anything that happens multiple times, or there can be multiple modes in a data set. So something like this would be a bimodal or multimodal data set. So finding the modes here, this one you can see that 0 occurs more than any of the other numbers, so 0 is our mode. But this one, however, you look through there and none of those occur more than any other number, so you would have none as your mode. Now 0 and none are two different answers, okay? So if the mode is 0, that means that 0 was in the data set and occurred multiple times. But if the mode is none, then that means there's just no mode. Okay, so sometimes students, if there's not a mode, they might put 0 because they're thinking of 0 as being none. But remember that 0 is an actual possible answer. So if there is no mode, make sure that you select that there's no mode as your answer. Down here you see we have multiple modes. 2 and 5 are both repeated 3 times, which is the most of any number. So 2 and 5 are your answer there. And the mode can be used with qualitative data. Most of our statistics or parameters that we talk about here are just going to be for quantitative data, but this can be actually used for qualitative data. Like if I wanted to know if these were, let's say, test scores, and I wanted to know which one occurred the most frequently, we would see that B, of course, would be our mode because most students made a B, or more students made a B than made any other letter grade there, so the mode would be B. There's some examples of calculating a mean and a median. Are we going to use the mean or the median? Okay, so why do we have two data sets, or why do we have two statistics, the mean and the median? Why don't we just, stick with one over the other? Well, in many cases, using the mean or the median's not going to matter. They're going to probably be pretty close to each other. But there are going to be situations where we would rather use the mean or rather use the median. And the cases where we'd rather use the median is anytime you have skewed data. When we have skewed data, our mean is going to follow that skewness. So you notice that if we have a skewed left distribution, which means most of our data is high, okay, so most of our data falls over here, and then we either have a few low outliers or we just have, this kind of trailing off to the left there to the lower numbers. The mean is going to follow that skewness or follow those outliers. So what that means is that the mean is going to give us not a very good representation of the data. It's going to look lower than what most of the data actually is. The median, however, will not be affected by those lower outliers, and so it's going to give us a better description of what the data actually is, okay, or where the data is actually centered. So that in that case, we'd rather use the median, okay? In this case as well, if we have a skewed right distribution, the median is going to be closer to where most of the data is. The mean, on the other hand, is going to be pulled up by those higher outliers, so we'd rather use the median. Now, if we've got a symmetric distribution, the mean and the median should actually be equal to each other if it's exactly symmetric. Now, if it's roughly symmetric, where what we're going to see more in real life data, we might not see that perfectly symmetric, but we'll see a roughly symmetric distribution or approximately symmetric, and so the mean will be approximately equal to the median. In that case, we would rather just go ahead and use the mean, mainly because most people that haven't had statistics in real life understand what a mean is. They know the mean is the average, so that makes sense to them. So using the mean makes more sense in the general population than trying to explain what a median is. All right, so if we have a skew distribution, use the median. If we don't, then go ahead and use the mean. So here's some more examples, and we'll get to doing some examples in a second. This was just some real life data. This is what the distribution of annual household income does actually look like in the US. It's always going to be skewed right. And that's just the case because we're always going to have those very few people in the population that tend to make a large amount of money. So you see here, this is 200,000 or more. So any of those millionaires, billionaires, they're all going to fall in this category. As those people continue to make more money, that's going to skew this distribution even more. So it might pull the mean up because those richer people are making more and more money, but that doesn't necessarily mean that most of the people in the US are feeling that increase in their salary. So if we were to say that the mean salary increased $5,000 in the last year, that doesn't necessarily mean that our economy is getting better. Okay, that might just mean that those millionaires and billionaires are making more money because the more money they make, the higher they're pulling that mean because that mean is following those high outliers or following that skewness there. So you notice that the mean is around 71,000, whereas the median is just about 50,000. So the median is a better representation of where most people's household income is. So if you ever hear on the news or whatever them talking about household income and all that, you always want to listen for the median and not be listening for the mean. If they tell the mean, you kind of just want to know that, well, that's going to be somewhat of a skewed number. So we're more concerned with if the median income has gone up versus if the mean income has gone up. And that's just some more information there, when to use the mean and the median. All right, so now what we've talked about is where the center of the distribution is, okay? So I know that my data is centered around, let's say, the number 10, okay? Well, I could have two different distributions, both centered around 10, right? So I could have one that maybe looks like this, and then I could have one that looks like this. Okay, and I could have another one that looks like this. Okay, so these are all kind of centered around 10. But there's something different about them, right? They don't all look the same. So what's making them more spread out or less spread out is talking about the dispersion of the data. So we want to know, okay, I know the data is centered at 10, but how spread out is the data? Is the data all really close to 10? Or is some of them close to 10 and some of them really far away? You know, we want to know about how the data is dispersed. There's two ways we look at dispersion. One is range. That's one of the easiest ones to calculate, and it just kind of gives you a quick idea of how spread out the data is. The range is just the maximum number minus the minimum. So you take the largest minus the smallest, and that's going to tell you, you know, do I have a range of 10, a range of 1,000, a range of 10,000? It just gives you a general idea of how close are my data points to each other. The standard deviation is obviously much more complex than calculating the range. I don't expect you to do this by hand. If you're doing this by hand, then you need to figure out how to do it on your calculator or using StatCrunch. This is going to be very time consuming by hand. I mean, it's great if you want to learn how to do it by hand. I do have an example in here of how to do it by hand, but because you have time constraints trying to do this on your test or trying to do it on a quiz or your homework, it's just better to try to do this using technology, okay? So we've got two different standard deviations. The population standard deviation, so this is going to be our parameter, is represented by sigma. The sample standard deviation, which would be our statistic, is represented with S. Okay, so S is going to be our sample standard deviation. That's usually what we're going to be working with is the sample standard deviation. Sigma is our population standard deviation. You might also notice sometimes in your homework problems, they'll talk about variance. Variance is really just the standard deviation squared. Okay, so sigma squared is how we represent the variance. So if you already have sigma and you want to find the variance, you just square it. If you have the variance and you want to find the standard deviation, then you take the square root of it. Okay, so they are related in that way. The same thing with the variance of the sample. your sample data. The sample variance is S squared, the sample standard deviation is S. The way we are going to find this, if you were to do this by hand, we're going to take each observation, so that's what our x sub I is, subtract the mean, so we have to find the mean first, okay? We take each observation, subtract the mean, we find all those differences and square them. Okay, so square each of those differences, then sum all those squared differences together, divide by n minus 1, and then that would give you the variance. But once you take the square root, that gives you the standard deviation. Okay, and that's how we will do that. These just go through trying to understand what standard deviation means without calculating it. So when I just look at these standard deviations and try to match them with these data sets, if I'm looking for which of these has a standard deviation of 0, we would choose data set 2. And that's because these data points don't vary at all from each other, right? So they have no variance or no deviation. So the standard deviation would be equal to 0 here. The standard deviation of 4 or standard deviation of 150, this would have a standard deviation of 150 because you see it's very variable, right? Those numbers are a lot different from each other. These are not as variable, so they're going to have a fairly small standard deviation. So what this is supposed to help you with is just understanding if you get a mean of this and a standard deviation of this, understanding what a large standard deviation would make your data look like, okay, or what your original data set is going to look like if you have a certain standard deviation. Our standard deviation is always going to be between 0 and then positive infinity. It can't be negative, mainly because of this. You're taking the square root, so you're not going to end up with a negative number, right? So the closer to 0 you get with your standard deviation, the less variation there is in your data. What that tells us is the closer our data is going to be to the mean, right? So if you have a small standard deviation, then our data is going to be really close to whatever our mean value was. It's saying it's not going to differ very much. And these are some other examples of that. This is how to actually calculate it by hand. I always kind of do it in a chart form. I write down all my observations again. These are all my x values. I calculated my mean in the first step. So here I'm subtracting each observation from the mean and getting this difference. I square the difference here. I sum those squared differences and get 98. That 98 now goes back up here because the 98 was the sum of all those squared differences, okay? Then I divide by 6 minus 1 because that was our n minus 1. Our n is sample size. 98 divided by 5 is 19.6. I take the square root and I get 4.43. Okay, so what statistics do we have now? The statistics we have talked about are x bar and s. The parameters are mu and sigma. These are the statistics we're going to use to infer about our population parameters. How are we going to do this in our calculator? Okay, let me pull up my calculator here. Let's see if I can, oops, do that. Sorry about that. Okay, for our calculator here, what we're going to do, if we just want to do just this simple data set here, let me turn this on. I'm going to go to stat and edit. That's always where I'm going to go anytime I want to put my data in lists. So anytime you have data that you're wanting to do something with, whether it's for this one variable statistics or for in chapter 4 doing linear regression, we go to this data set in the stat area. So stat edit. Now I'm going to put my data in list 1. If you already have data in your list and you want to clear them, just go up and push clear and enter, and that will clear out that entire data set instead of you having to go through and do delete, delete, delete for each little observation. So I'm going to put in 2, 5, 7, 8, 12, and 14. So I'm just using this data set here. Okay, now I'm going to go back to stat and I'm going to go over to calculate and I want to do one variable stats. Now after the one variable stats, if yours looks like this, you're going to go in and put L1. Your screen may look a little different, but you just want to say that the data list, your data is in L1. So you will put that into your calculator. And then you get this output. So with this output, you get the mean. This gives you the sum of all the x's, the sum of the x's squared. We don't really use those, but you could use them in different formulas. That's why they give you those. S sub x and sigma sub x. So this is our sample standard deviation. So if our original data set was a sample, then we want to use this. Generally, we are doing data that's a sample. So we usually want to use the S sub x. The sigma sub x is going to be the population standard deviation. So you'll use that if you happen to be dealing with a population. N is our sample size. Then notice that this has an arrow, so we can arrow down and get more information. When we arrow down, that's where we can find the median, which it says here is 7.5. And this is actually, these five numbers together are called our five-number summary. And that's what we're going to get to in a few slides, the five-number summary. So using just those one variable stats pretty much can answer most of the questions that you're asked about in chapter 3. So that is very helpful to use. Okay, then we've got some empirical rule and Chebyshev's rule stuff. The empirical rule is very important because the empirical rule is something that we will actually use moving forward. We will use it again in chapter 7, 8, 9, and 10. So if you can understand it now, that will be helpful to you. So the empirical rule just tells us that we have 68, it's also called the 68, 95, 99.7 rule. For any data set with a roughly bell-shaped distribution, so we're talking about symmetric distributions here, approximately 68% of the data is within one standard deviation, 95 is within two, 99.7 is within three. For Chebyshev's rule, we're using this for any distribution, mainly for the skewed distribution. So if you know nothing about your original population, you would want to use this, or if you already know it's skewed. So like if you're using the annual income data, you already know that's going to be skewed. So you would want to use the Chebyshev's rule. What it tells us is at least 100 times 1 minus 1 over k squared percent of the observations lie within plus or minus k standard deviations of the mean. So I know that doesn't make a lot of sense, but what that means is if I wanted to know, let's say within 2 standard deviations of the mean, okay, I plug in a 2 here for k. When I plug in that 2, I get 75%. So that tells me that at least 75% of the observations are within 2 standard deviations. If I want to know within 3, I'd plug in a 3 here and I get at least 89% are within 3 standard deviations. So that's how you're going to use those. Here's how we use that empirical rule. When we get the mean, they give us the mean probably in our problem. That's going to go right in the center here. So that's our middle, because remember that if we've got a symmetric bell-shaped distribution, the mean and the median are equal to each other. So that's going to be right in the middle there. We've got a standard deviation of 2.2. So I'm going to add and subtract 2.2 3 times. Okay, so I added here and got 66, add again, add again. Here I subtract, subtract, subtract. And I only do it 3 times because the empirical rule only goes up to 3 standard deviations away. After that point, we're not really concerned because very little of the data falls outside of there. So then we can do the rest of this using this chart that we created, and that'll help us to answer the rest of those. Measures of position is when we get into actually doing the 5-number summary. I showed you how to do that on your calculator. This is how to do it by hand, but obviously it would be easier to do on your calculator. This is how to identify outliers. You can use these lower and upper fences to tell if you have an outlier or not. So once you find your Q1 and your Q3, you can find the interquartile range, which is just Q3 minus Q1. You can plug that in. And then you can figure out if your observation falls above or below that upper or lower fence, and that will tell you if you have an outlier. Another easy way to find out if you have an outlier is to construct a box plot. You can do this on your calculator fairly easily. I think I have a slide for that right here. Let's say we've got, let me pull up my calculator here again. We've got some data in here, just a very small data set. But if I wanted to go in there, I've already put my data in, the data I had in there before. I go to second y equals, that's where my stat plot area is. I'm going to go to number 1. First, I want to turn it on so it'll actually show up on the graph. There's 2 different box plots. The first one here you notice has dots beside it. That means it will show if there are outliers, and if there are, it will represent them by little dots. This one here, though, if there are outliers, it doesn't show them special. Okay, so if the maximum number is an outlier, it's just going to show it as the maximum. Okay, so you would use the first box plot to be able to identify if you have any outliers. The second box plot could be good if you're just wanting to know the shape of your distribution. So we're going to use this dot one there. The X list is saying where is your data at. Mine's in L1. We don't have a frequency list. This is it's just going to how it's going to mark the outlier. And then we go to graph. Now, if you can't see it at all, or if you have it where it's only showing you partial, you want to go to zoom. And then for the stat plot one, we want to use zoom stat, and that's what we want to use anytime we use the stat plot. So when we're doing this in chapter 4 for linear regression, or if you're doing a histogram, or you're doing something else in there, if you use the stat plot, go to zoom stat. So that's number 9. And then you get this nice view of it. Now ours didn't have any outliers, so we don't see any dots there. So if you're trying to figure out if your data had any outliers, you could do this. If you see those outliers marked with dots on there, then you would know that yes, I do have an outlier. Now how would I know what these data points represent? I can go to trace, and you see here it says this first point is the minimum value, which is 2. Then Q1 is 5, the median is 7.5, Q3 is 12, and the max is 14. So that gives you your 5-number summary, and you can use that as well. The box plot is just a graphical representation of the 5-number summary. So you basically have these 5 points here, and those are your 5-number summary. Okay, the last thing we deal with in chapter 3 is this standardized variable, which we also call the z-score or just the z-value. This is going to be very important also moving forward. We just deal with it just a little in this chapter, but we will return to it in chapter 7. When we start talking about the normal distribution again. So the z-score here is going to be one way that we can compare distributions. So what the z-score tells us is how many standard deviations an observation is from the mean. So if I have a z-score of 1, that tells me that my observation is 1 standard deviation above the mean. The z-score can be positive or negative. We expect the z-score to be between -3 and 3, and that is because of this. Okay, with the empirical rule, we said that within 3 standard deviations, 99.7% of our data falls. Okay, so outside of 3 standard deviations from the mean, we're not going to expect much of our data to be out there, right? We're only going to expect about 0.3% of our data to fall farther than 3 standard deviations away. So when we're doing the z-score, since the z-score tells us how many standard deviations we are from the mean, we're going to expect it to probably be between -3 and 3, because we shouldn't expect most of our data points to be any farther than 3 standard deviations away. So you see here, I just found the z-score. It's a pretty simple formula. You do x minus mu over sigma. So you're taking your observation, subtracting the mean, dividing by the standard deviation. But how we can use this in a practical sense is we can use it to compare distributions. So for example, if you took the ACT and your friend took the SAT, you're going to have totally different scores, right? But how are you going to know who scored better relative to their test? One way we could do that, of course, is maybe using percentiles. Like let's say when you get your test printout, they usually give percentiles, and so you might know who did better based on the percentile. But the z-score would also tell us that. Z-scores are similar to percentiles, and we'll talk more about that in chapter 7. But here we'll calculate Jenny's z-score. She got a score of 600 on the SAT. The SAT has a mean and standard deviation of 500 and 100. So her z-score is 1. That means she scored 1 standard deviation above the mean. For Mike's z-score, he got a 21 on the ACT. There was a mean of 18 and the standard deviation of 6 on the ACT. So his z-score equaled zero point 0.5. So he was zero point 0.5 standard deviations above the mean. So you can see that one standard deviation is farther away than half of the standard deviation. So in this case, a larger z-score is better because that means you scored higher, right? So that would mean that Jenny had the better score. Okay. And then that is the end of chapter 3. So what I want you to learn from chapter 3 is making sure you know how to do these calculations in your calculator. So using the one variable stats, or the other thing we talked about is on my prior one is that you could also do this using the stat crunch. So let me move this real quick. The stat crunch, you can always go to here. You can open something in StatCrunch. Now this data set I'm actually going to use in chapter 4, but if we wanted to use that here, we can go to Stat. We want to do summary statistics. And we're going to do columns. Usually the data is there in columns. So let's say I'm just going to choose Y. Um, and I want to find all this stuff. So you notice there it already has what you would need for the 5-number summary. It has the mean, it has the standard deviation, the variance, some other stuff you may not need, but all that should be fine, okay? And then we'll store in a data table and compute this. And so here we've got the standard deviation, we've got the median, the range, the min, the max, all the information that you might need. And so it's all there for you. I mean, you can use it that way. The StatCrunch is going to be it's available on every quiz, every test. It'll also be available on the final exam. So you can use that StatCrunch if you like that better, or you can use your graphing calculator as well. All right. So if you have any questions about this chapter, please get back with me and I'll help you however I can. Thanks.